Okay, so hello everyone. Welcome to this kind of mini tutorial. I'm gonna hopefully post this by the end of today. Hopefully a bit before, hopefully a bit before tonight, so you can have some time to skim over it, and maybe it can be helpful for you to do your assignment. Okay, so I'm not going to use any slides because I didn't really have time to put some slides together, but basically, the first topic of this tutorial is going to be converting regular grammars to FAs and the other way around. Okay, so the first direction when you want to convert a regular grammar to a finite automata. So let's say you have a grammar G with variable set V, terminal set T, start variable S, and production rules P. Okay, how do you convert this grammar here to an FA? Okay, well, it's all in the structure of the production rules. So for the initial state of your FA, the initial state is the start variable. So it's always going to be the start variable. And then the production rules become your transitions. So let's say, because this is a regular grammar, and for the purpose of these slides, we're going to assume a regular grammar is right linear, even though it can either be right linear or left linear. I'm just not going to cover left linear for the sake of time. But let's say you have a production rule that looks like one variable on the left, and then a string of terminals, and then another variable on the right-hand side. Okay, so X here is any string over the terminals T, so that's why it's in T star, and then A and B are both variables. So we have this production rule. How do we convert it to a transition? Well, you essentially make your variable a state, and you make your variable B another state. And then if X is, for instance, X1, X2 until Xn, where each of these Xi's are in T. So in other words, X could be something like AB, BA. So for example, if the terminals are AB, then X could be something like AB, BA. Then what you would do is, for each symbol, you would make that a transition to an intermediate state, basically. So for instance, if I had a transition that looked like, a production rule that looked like the variable A on the left-hand side, and then A, B, B, A, B on the right-hand side, then this would be converted to the state A, and then transitions A, B, B, A, and then another state for my variable B. Okay, so it seems pretty natural to convert this production rule to this kind of transition. If instead of having a variable at the end of your string of terminals, you have no variable, then it's only slightly different. The difference is that you again make your variable here a state in your transition graph, but now you're going to end up in a final state. So because here there isn't a variable, that variable means that the lack of variable means that this production rule is going to lead you to a final state when this is a regular grammar. Okay, so if, for example, I had something like, so let me write this in blue. If, for example, I had A gives you AB, then you would have your state A, and then you would see a B, and then see an A, and then see a B, and then end up in a final state. Okay, so let's do an example. Suppose you have the following grammar G, where there are two variables S and A. The terminals are over A, B, and the start variable is S. And you have the following production rules. You want to convert this to an FA. So it can either be a DFA or an NFA, as long as it's a valid finite automata. Okay, so In this case, this is an example we've already seen. And if you go back to tutorial 5, this was actually the language accepted by G was in fact all strings over AB star such that W contains the substring AB. So any string that contains AB as a substring. Okay, so what should happen then is we should get a very familiar FA when we convert this regular grammar to such an FA. Okay, so in this case, I'm only going to have two states because I'm going to have initially two states, S and A. So I can draw my state S as the initial state and my state A on the right. And now I go through each of the production rules individually. So this one here tells me that S gives me AS. So I have a transition when I see A. If I'm in S and I see A, I go back to S. So that's the same as a self loop on S when you see A. And there's also going to be a self loop on S when you see B. Okay? Then we have another transition here. S gives you ABA. So this is a transition that looks like S gives you ABA. So now I need an intermediate state. So I'm going to read an A and then get to an intermediate state, and then read a B and then get to A. Okay. And then finally with my A, if I'm in A and I see a little a, then I can go back to myself. So that's a self loop on A. If I'm in A and I see a B, then I go back to A. So that's another self loop. And if I'm in A, then I can also just give myself a lambda. So remember a production rule that looks like, so this is like a production rule that looks like A, x1, x2, so on, xn. So that would, in sort of in general, that would just look like A, and then you have a bunch of transitions until some final state, okay? But in this case, all of these x1s are like lambdas, and so in fact, you're going to not create any new states and just make A final state. So then A becomes a final state. And now we can clearly see that this is a very natural NFA that someone might have written if they wanted to accept all of the strings that contained AB as a substring. Okay, so this would be your converted FA. Okay, now let's do another one. So here I have a grammar G over 3 variables, ABS. I have terminals AB, and I have my start state S, and I have the following 3 production rules. So remember, each variable on the left-hand side becomes a state, and my start variable S is going to be the initial state. So I start at S, and then in this case, this is like lambda A. So it's like I have a lambda transition to my state A. So now I'm in A, then I can get another lambda transition to B. And then if I'm in B, I can get another lambda transition to S. Okay. And this actually can just be this is equivalent to just the NFA S. And this is actually the NFA that accepts. So if this is M, the language accepted by M is the empty set. And this is another reason why a grammar that looks like this, because the grammar generated by G is the same as the language, the language generated by G is the same as the language accepted by M, which is the empty set. Okay. So now that's for converting a regular grammar to an FA. What about the other way around? So if you have an FA, then you can always convert it to a regular grammar. In this case, we only consider right linear grammars. For left linear grammars, please look at your lecture slides. So it's again kind of the same process, except that now so now remember we're dealing with FAs and we're going to a regular grammar. So each state in your FA becomes a variable. So each state becomes a variable. And then if you have a transition like this, where if you're in Q and you see A, you go to P, then that becomes the rule Q gives you AP. Okay, because this is like, you can read this as when you see a Q in your derivation, then you can replace it with AP. Okay, and here P is the variable and A is the terminal. If you're in a final state, then the way you could convert this is you could say that if you're in Q, then you can see a lambda basically. So you can replace that with a lambda, right? And that would sort of be the way that the derivation would end in your grammar. And finally, for your initial state Q0, this becomes the so if you have a grammar G with variables V, terminals T, then your start variable is going to be Q0, and you're going to have some productions that come from the transitions. Okay, so let's look at an example. Suppose I have the following FA, and I want to convert it to a regular grammar. So again, for the purpose of this tutorial, we're just going to consider a right linear grammar. So if I want to convert this to a right linear grammar, remember all I need to do is convert all my states to variables. So let's say I have a grammar, I get a grammar G, then the set of variables is going to be the set of states. So Q0 until Q4. The terminals are going to be essentially the alphabet that we see is the alphabet for this FA. So in this case, we only have A and B. Remember, typically you don't really include lambda in your alphabet because that just means the empty string. Okay, so your terminals are going to be A and B. Your start variable is going to be Q0. So all derivations, like all paths in an FA, start with Q0. And then you're going to have some production rules P. And the production rules P are going to be listed as follows. So let's start with Q0. If you're in Q0 and you see an A, then you can either go to Q1 or to Q2. So you can write that as Q0 when it sees an A goes to Q1, or Q0 when it sees an A goes to Q2. And then if you're in Q0 and you see a B, you're in Q0 and you see a B, then you go to Q2. Then let's do it for Q1. If you're in Q1, so if you're in Q1 and you see a B, then you go to Q4. You see a B, you go to Q4, and that's it for Q1. Then if you're in Q2 and you see a B, then you self loop back to yourself to Q2. If you're in Q2 and you see an A, then you go to Q3. And now for the final states. So Q3 is a final state. So we can immediately write that Q3 goes to lambda. And then we also see that there's a self loop on Q3. So when you're in Q3, and you see an A, then you go back to Q3. And the last one is a lambda transition to Q1. So you could just write lambda Q1, but really this can just simplify to, if you see Q3, then you can go to Q1, okay? And finally, for Q4, there aren't any outgoing edges. So the only thing you need to do is to make sure that this is a equivalent final variable in a sense. So that's why you say Q4 gives you lambda. And then this is a set of production rules that is going to generate the same language accepted by this guy. So then in general, if you're given a question like, so for example, if you're given a question like find the grammar G such that the language generated by G is a particular language L, then instead of directly finding G, what you could do is you could first you find an FA M such that the language accepted by M is L. And then the second thing is you take your FAM and you convert it to a equivalent grammar G. And then the language accepted by G, the language, sorry, not accepted, the language generated, right? This is a very important concept to remember. Grammars generate languages. The language generated by this grammar G is going to be equal to the language accepted by the FAM, which is going to be the language that you want your grammar to generate. Okay, so next off, we're going to look at the very ominous pumping lemma. Okay, so let's look at the pumping lemma. Okay, so first I'm going to sort of read to you very basically what the pumping lemma says, and then I'm going to try to explain to you how it's used to show that a language is not regular. Okay, so we have the following lemma. The lemma is just like a smaller theorem in a way. So if we have an infinite language L, so just that's a very important point to note, that this does not work if L is finite. So this cannot be the case. And then if L is finite, it's already regular. So just don't worry about that. Just let's assume that you have an infinite language L, okay? Then if we have such a language L, and this language is, and L is regular, okay? So if L is an infinite language that is regular, there exists a natural number M such that for every string in your regular language L, where the length of that string is at least M, we can decompose this string into three parts: X, Y, and Z, where the length of X and Y is less than or equal to M, and the length of Y is greater or equal to 1, such that, and this is the key such that, there's a lot of such that's in the pumping lemma, but basically, if you're given all of these conditions where you have that W can be decomposed into X, Y, Z, then for every integer I greater or equal to 0, then X, Y to the I, so in other words, X, then Y, I number of times, Z should also be in L. Okay, that's what the pumping lemma says. And so what is the use of the pumping lemma? The only use of the pumping lemma is to show that a language is not regular. If the pumping lemma is true, so in other words, if this pumping lemma here, if this guy here is true, it does not prove that the language is regular. You can only use the pumping lemma to show that a language is not regular. Okay, so how do we do this? Well, we use what's known as a proof by contradiction. Okay, so suppose you're given a language, you're given a language L, and your goal is to show that it is not or non-regular. Okay, that's what you want to do. Then what you do is you assume, for the sake of contradiction, that L is in fact regular. If L is regular and L is infinite, okay, then this condition here, so all of this condition after the blue bracket here up until here should hold, okay? So what we're going to do is we're going to show that it doesn't hold, which leads to a contradiction. So what you need to do two picks, two very clever picks in the pumping lemma to get a contradiction. The first thing you do is you pick a particular string W in L. And that string must have length at least m, okay? So now that you've picked this string W, so you know that this string W has length at least m, and so now according to the pumping lemma, it can be decomposed into x, y, z. So each of these are strings where you know that the length of x, y is less than or equal to m, and the length of y is at least 1. Okay? So this is not something that you choose. This is something that's given to you by the lemma. So far, the only thing you've picked is a string. So you've picked a particular string with length at least m. And then what you do is you pump. So you pump up or you pump down by picking. So this is the second pick where you pick an integer I. So I should specify that I is an integer, and that integer is greater or equal to 0. So you pick such an integer I where you pump, when you pump the y I number of times, then L, then this guy here, Wi, we denote it, won't be in L, okay? And this will lead to a contradiction, okay? Why is this a contradiction? This is a contradiction because this pumping lemma here, the lemma here, a lemma is a theorem, so it's something that's been proved to be true for regular languages. This lemma says that if you have a regular language and that it's infinite, then this condition here where Wi is in L should be true for every I greater or equal to 0. So what you've done is you found a particular I and a particular string where this is not true, so this contradicts the lemma. Okay, so far this is very abstract. Let's do a first example to make that more concrete. So I know that he's already shown that the language ANBN is not regular. This is going to be a very similar example, okay? But I essentially want to show you the steps that you take to get to the conclusion that L is not regular. So we have the following language here, L, which is ANBKCN. So any number of A's followed by any number of B's followed by any number of C's, where the number of A's is the same as the number of B's. So in a way, you can already see that this is very similar to ANBN. The only difference is that you have some B in between, but that number of B's is unrelated to N, okay? And your goal is to show that this is not regular. So how do you do this? Well, the first thing you do is you know that L is infinite. So what you do is you assume for contradiction, you assume for the sake of contradiction that L is regular. So because L is regular and because L is infinite, then the pumping lemma should hold. So now we're going to try to break the pumping lemma by picking a particular string and a particular I. Okay, so let's pick a string. So now the second thing I need to do is I need to pick a string W in L such that its length is at least m. So there's always sort of a different pick for W that could happen. Typically with some practice, you start to see the sort of best tricks to pick W. In cases like these, so in the case where I have a string like this, what you want to do essentially is you want your first first, so remember what we're going to do at the end. So this is sort of like a sneak peek. At the end, we're going to have W as X, Y, Z, and then we're going to pump up or pump down Y. So you want to try to find a string W where when you pump up or down Y, this is going to not be an L anymore, okay? So one very natural pick here is going to be, I'm going to pick W as AM, CM, okay? So you're going to ask, what about the K? Well, here it's given that the K is greater or equal to 0. So in this case here, my K is equal to 0. And that's not a problem. So this string W is an L, and it most definitely has length at least M, because in fact, it has exactly length 2M, which is greater or equal to M. So what I have now is I've picked my string W that has the form AMCM. Okay. So the third thing I need to do is I need to pump up or pump down to get a contradiction. But before you do that, it's good to break down your string W. So what does your string W look like? It's a bunch of A's and then a bunch of C's, where there's MC, MA's and MC's. So W looks like A, a bunch of times, A. So M times. And then it looks like C, M other times, okay? And now the pumping lemma tells us that we can decompose this string into X, Y, Z, where X, Y is less than or equal to M, and not Z, Y is at least 1. So this tells us that the XYs are within the first M symbols of W. So that means that my XY, so my X is going to be somewhere here, and my Y is going to be somewhere here, but it's not going to go past, my Y is not going to go past here. So it's never going to be within the C's, because then XY would have length greater than M. So because XY has length at most M, I'm going to write X is some A's, Y is some other A's, and maybe it goes until the end, or maybe it stops a little short. And so the rest of this is going to be Z, okay? So what this tells us here, this tells us that Y is equal to some number of A's consecutively. So let's not write K, let's write, what's a good letter? Let's say R. So there's R A's in a row that compose the Y. And because we have this second condition here, that Y, the length of Y is at least 1, then we know that R here, which is the number of A's in Y, has to be at least 1. Okay. So what does that mean? That means that W is in fact going to look like a bunch of A's, and then we can say A to the R, okay, and then maybe a few more A's, and then so there's M of these, and then M of the C's, okay. So now what we need to do is, okay, so now I'm going to erase this to make it clear. So now what we need to do is we need to pick an I to pump up or down Wi. So remember, Wi is going to be X, Y, Z. Okay, so let's say really actually any pick for I except for 1 here is going to work. So let's say I pick I equals 2. So W2 is X, Y squared Z. Then this means that this means that this y here is going to become y square. So you're going to get a2r. Okay, so then your string w2 is going to have MAs from the original XYZ, and then it's going to have an additional 1R of A's, okay? Only one, because remember before, so remember initially, so W1 is really W1 is something like some A's and then A to the R, and then some A's and then some C's, okay? So what I'm going to do now is W2, all of this is M, right? There's M symbols there. Then I'm going to add another RAs. So I'm going to have A, and then AR, AR, and A, okay? So then you can think of it as this and this. So maybe if I zoom in, yeah, okay. So you can think of it as this guy and this guy being MAs, and then you add an additional RAs to that. So that's why here, let me zoom out again now. So that's why here you have M plus RAs, okay? And then the number of C's is going to remain unchanged. So you're going to get AM plus R, C to the M, okay? And we know that this is not in L because we know that the strings in L are going to look like the same number of A's as C's, but because R is greater or equal to 1, we know for sure that the number of A's here is different from the number of C's here. So we know that M plus R is different from M. So that means that W2 is not in L, which is a contradiction. So that means that the initial assumption 1 here, where we assume that L was regular, was false. And in fact, this shows that L is not regular. And I like to finish the proof with a little box. Okay, so hopefully that's been clear. This is very similar to the example the professor shown, but I'm just sort of repeating it in case you wanted to have a different perspective on it. Okay, another type of showing its non-regular question is where you have a more generic kind of string where you don't have a certain structure, but you're given, in this case, you're given the strings WW. So for instance, AAB, AAB. So that would be an L, okay, because you can split this into two identical strings, okay? And you want to show that this is not regular. So this is very similar to the previous example. No, not the previous example, but an example that the professor showed with WWR, okay? Except that your W that you're going to pick is slightly different. So let's do it. Let's apply the pumping lemma. So first, assume that L is regular. Okay, you assume L is regular, and you know that L is infinite. So now we can apply the pumping lemma. Okay, so now what I'm going to do is I'm going to pick a string W in L such that the length of W is at least M. Okay, so there's again a couple of, there's actually infinitely many picks that you could choose. But one that I know will work in this case will be W equals A to the M, B to the M, A to the M, B to the M. So we have the same string twice in W. We have AMBM and then AMBM. Okay, and now we've picked a string W, and for sure the length of W, which is actually 4m, is at least greater than m. So now we can move on to the pumping step. Okay. So now what I need to do is I need to pick an I such that Wi, which is x, y, I, z, is not in L. Before you do that, it's always good to start by decomposing your W into x, y, z. So let's do that. We have W is AM, BM, AM, BM. So we have a bunch of A's. Okay, so we have M of those. Then we have a bunch of B's, a bunch of A's again, and a bunch of B's again. So we have M of those, M of those, M of those. Okay. And remember, W is decomposed into X, Y, Z, where the length of X, Y is less than or equal to M, and the length of Y is at least 1. So what this tells us is that the XYs are within the first M symbols of W. So the XYs are within the first M symbols of W. And actually a very sort of a trick for picking W is that you want your XYs to be sort of part of the same component of your string. So you want the XYs to be, in this case, all A's. That's a good trick. It's not always going to work, but in this case, it will. Okay, so what does your X look like? Your X looks like a bunch of A's, and then your Y looks like a bunch of A's, and it can't go sort of further and have some B's because then its length would be greater than M. So we know that it stops, maybe it stops at the last A, or maybe it stops here. So without loss of generality, let's just assume that it stops here, okay? And then, so the rest of your string is going to be Z. And in fact, you never really think about Z, you're mostly just thinking about your Y and also your X, okay? So in this case, again, you have that Y looks like a bunch of A's, so I'm going to write A to the R. And because of this second assumption that the length of Y is at least 1, you know that R here has to be at least 1. So now what you need to do is you need to pump up or pump down. So before I pumped up, so now I'm going to pump down. So what I have now is I have W1 is A to the M, B to the M, A to the M, B to the M. So if I pump down, then I need to pick I equals 0. So I get W0. And what's going to happen now is, let me pick this. So from the M A's in the beginning, you're going to remove A to the R once. So pumping down would mean that you get pumping down. So W0 would be X, Y to the 0, Z. So you're removing your Y once, okay? So then what you would get is A to the M, and then remove R of those from Y, and then B to the M, A to the M, B to the M. And here we clearly see that this sort of first half, so if you can find the first half of the string, is going to look very different than the second half of that string, okay? So we here see again that the pumped string is not in L, which is a contradiction. This is a contradiction, and so this implies that L is not regular, which completes the proof. Okay. Okay, and the last example that I'm going to show you is another different kind of non-regular language. It's one where you have only a bunch of A's, but the number of A's has a particular restriction that is going to make it very difficult to be regular. So we want to show that this following language, L, where L is all the strings that where the exponent of A is equal to 2 to the K. So in other words, L is A 2 to the 0, A 2 to the 1, A 2 to the 2, and so on, A 2 to the K, and so on. Okay, we want to show that this is not regular. How do we do this? Again, same idea of pumping lemma. We first assume that L is regular. Okay, so L is also infinite, so now we can apply the pumping lemma and try to break it. So the second thing we're going to do is we're going to pick a W in L such that W has length at least M. So a pick here that is going to make sense is going to be A to the M. So if we pick W is equal to A to the M, okay, where by definition, okay, where because we want W to belong to L, M is going to be equal to 2 to the, let's say 2 to the K for some K. Okay, so M is a power of 2 for some power. Okay, then W, which is equal to A to the M, is for sure going to have length at least M. Okay, so I've picked my string W, and now I want to break the pumping lemma by pumping up or down and showing that this pumped string will no longer be part of L. Okay, so in this case, for W, so in this case, if W is not part of L, what I could do is I could say that W is equal to some A to the C to the T, where T is not equal to a power of 2. So that's what I'm going to do. I'm going to try to find a pump, an I, a pump up or a pump down, where when I pump up, this assumption that T is a power of 2 is no longer going to hold. Okay, so let's try an example. Well, no, let's actually do it. So if I have my string W, then remember I decompose it into X, Y, Z. And here it's pretty easy to see what Y is because it's the same as X and it's the same as Z. W is just a bunch of A's, M times, okay? And then we know that within the first, M's, we have X, Y. So maybe this is my X and this is my Y. So Y is going to be equal to A to the R, okay? So remember, this assumption is because we know that X, Y is less or equal to M. And this assumption, where I'm going to write R is at least 1, is because we know that the length of Y is at least 1. Okay? So now what I'm going to do is I'm going to, in this case, I'm going to pump up. So I know that W1 is equal to X, Y, Z. So then W2 is going to be equal to X, Y squared Z. And that just means that I'm going to add an extra Y to my string. So I'm going to get, essentially, I'm just going to add RAs to my string AM. So I'm going to get A to the M plus R. Okay, and so the tricky part now is to show that M plus R is not a power of 2 to the K. Okay, and what I need to notice to show that is I need to notice the following, that in all of the previous sort of in all the previous examples, I've only said that R is at least 1. But there's going to be an implicit assumption here that R is also at most M, okay? And the reason for that is if R was larger than M, then XY would not be less than or equal to M, okay? So Y is equal to A to the R, and R is less than or equal to 1 and greater or equal to M, okay? So now, I have my pumped string W2 that looks like A to the M plus R. So now my goal reduces to more like just a discrete math problem. I want to show that M plus R does not equal 2 to the K for some K greater or equal to 0. Okay, so how am I going to show that? I'm going to use sort of an inequality argument. So I know that M plus R is larger than 2 to the K. Okay, why do I know this? Because remember, when I picked my string W, I said that W was equal to A to the M for some M equal 2 to the K. Okay, K can be greater or equal to 0. I wanted this to be true because I want W to be part of L. But now, because I know that because I know that R is at least 1, okay, then I know that M plus R is going to be, well, basically, M plus R is strictly greater than M, which is equal to 2 to the K, okay? So I know that it's larger than 2 to the K. What I'm going to want to show at the end, I'm going to want to show that it's strictly less than 2 to the K plus 1. So if I can show that M plus R, if I can show that M plus R is between 2 to the K and 2 to the K plus 1, then I know for sure that it's not equal to 2 to the T for some T, because there isn't any other K in between that could allow it to be a power of 2. Okay, so that's my goal. So how am I going to do this? Well, I know that M plus R is less than or equal to M plus M, okay? And let's see. Okay, so after thinking about it for a while, I actually see that what I've done is I've made a mistake in the M that I picked. And the reason for that is if I started the argument that I was showing you, and I wanted to show that M plus R was strictly less than 2 to the K plus 1, then it wouldn't have worked, because we had M plus R was strictly greater than M, because R was greater or equal to 1. But then I have that, I know that R is at most M. Okay, so I have M plus M. And then I know that M is equal to 2 to the K. So I would replace 2 to the K and 2 to the K for both M's. I would get 2 times 2 to the K, and that would equal to 2 to the K plus 1. So I never get a strict inequality. Okay, so that means that actually the pick for my M was incorrect. Okay, so this is an example of a pumping lemma where you would get an erroneous kind of pick, and it wouldn't lead you to the correct contradiction. So this does not lead to a contradiction. So this was actually not on purpose. I thought I had actually gotten it, but I didn't. So you see how easy it is to make a mistake in these cases. So let's try to redo steps 2 and 3, and I'm going to try another pick. Okay, so I have I start again at 2, and I want to pick a W in L. such that the length of W is at least M? Well, something that I should have thought about initially is even simpler to picking W equals A to the M, where M is a power of 2. I could have directly said W is equal to A to the 2M, okay? Because clearly now I have a power of 2 in A, and I know that 2 to the M is greater or equal to M. Well, actually, to show this, you would really need to use induction, but for the sake of this course, we can sort of assume that this is a true without a proof, even though really to be rigorous, you should prove that, but it's fine. So now I've picked a W that is equal to A to the 2M. 2M is greater or equal to M, so I know the length of W is at least M. And because my power in A is a power of 2, I know for sure that W is an L. Okay, so now what I'm going to do again is I'm going to try to pump up or down to see if I can get a contradiction. Okay, so that's what I'm going to do. So again, my W is a bunch of A's basically. Okay, I have 2 to the M A's. And within my first A's, within the M first A's, I'm going to get X, Y. So we clearly see that X is going to be uh, any number of A's where that number has to be at least 1, okay? And that's from the second condition. So the first condition is xy is less than or equal to m. The second condition is that y has to be at least 1, okay? And so that's why here the number of A's for y is at least 1, okay? So that's actually what W1 is. So what I'm going to do now is I'm going to pump up. I'm going to get W2. So I'm picking I equals to 2. And that's going to give me X, Y squared, Z, which is going to essentially allow me to add R A's to A to the 2M. So I'm going to get A to the 2M plus R. Okay, so now my new goal is, again, in the one where I made a mistake, is to show that 2 to the m plus r does not equal 2 to the, let me be consistent, 2 to the t for any t greater or equal to 0. So essentially this number is not a power of 2. And to do that, what I'm going to do is I'm going to show that 2m plus r is strictly greater than 2m, and that it's strictly less than 2 to the m plus 1. Okay, now that's going to be possible. So I'm going to again use the same assumption as before. I'm going to use that r is at least 1, and I'm also going to use the fact that r is at most m, because if r was larger than m, then y would have more than m a's, and then xy would be larger than m, which would violate that assumption. So that wouldn't lead you to a contradiction. That would just make that would make your initial sort of your if condition already false. So you wouldn't be able to do a proof by contradiction. Okay, so all of these steps need to hold for you to do a valid sort of pumping lemma. Okay, so this is my new goal basically. So now again, as I said, it boils down to some discrete math. So because I know that r is at least 1, I can say for certain that 2 to the m, so you can just think of 2 to the m as x, is strictly less than x plus r. So x is just 2 to the m, and r is just an r. Okay, because I know that r is at least 1, right? So then what I'm going to use is I'm going to use this property here. And I'm going to say that r is at most m, so 2 to the m plus r is at most 2 to the m plus m. Okay, and now I'm going to use an even stronger condition. I'm going to use the condition that 2 to the m is in fact strictly greater than m for any m greater or equal to 0. And you can sort of just convince yourself by doing a couple of examples. So 2 to the m and m, if m is 0, 2 to the m is 1, m is 1, 2 to the m is 2. And then you can sort of see just by exponential growth that the m is never going to catch up to the 2m anymore. Again, this should be shown by induction, but I'm going to skip that. And so what I'm going to use now is I'm going to use the fact that m is strictly less than 2 to the m, okay? So now I have a strict inequality, which is what I want. And 2 to the m plus 2 to the m is just twice 2 to the m, and that's 2 to the m plus 1. So what I've shown now, I've shown that 2 to the m plus r is between two consecutive powers of 2. So 2 consecutive powers of 2. So there isn't any room for this guy to equal 2 to the t. And so this shows that 2 to the m plus r is not equal to 2 to the t. Okay, so I've shown this. And so if I go back, well, let's say I bring my W2 down here. So this implies that W2 is not part of L because W2 does not have the form because W2 is not of the form a to the 2t for some t greater or equal to 0, which is a contradiction. Okay, so that shows that L is not regular. Okay, and that completes the proof. Okay, so sorry about making that initial mistake, but actually I think that was beneficial for both of us because we saw that you need to actually be fairly clever, and sometimes it takes some trial and error to see what the best pick for your W is and for your M. Okay, and the pick for I is usually, if you get the pick for W correct, it's often not going to matter that much as long as you remain a bit clever about it. Okay, so I hope I'm going to be able to upload this in time, and I hope some of you will be able to use this to help you in your assignment. All right, see you.